Hello everyone, welcome back to the new video lecture. This week in this video, we'll be talking about mathematical induction. Mathematical induction is a proofing strategy or proofing technique, right? It's a proofing technique or proofing strategies to prove different theorems or different claims. So let's understand that what does this induction means and how we are going to prove that. So it's we can consider this ladder and we can assume that we can actually understand this mathematical induction from this ladder. So assume that this is an infinite ladder, right? Infinite ladder. So what we want to do is I want to say that my claim is that I can go to any rung of this infinite ladder. I can reach to any rung of this infinite ladder. So how can I prove that? How can I prove that? You will obviously see me. So I can say that I can reach to the rung number one, which is my step number one. And then if I can reach to the step number one, from there, I can reach to the next step, next rung, which is a step number two. And from the rung number two, I can go to the rung number three. From the rung number three, I can go to the rung number four, right? Then if I can do that, then I can reach from that step by repeating those number of steps. What I can do, I can reach to any arbitrary kth rung. And then if I can reach to the kth rung, I can prove that I have to show that I can reach to the k plus one rung, any arbitrary rung, and then I can prove that I can reach to the k plus one rung. So that means in that way, I can reach to any of the rung of this ladder, right? That's how I'm going to prove. So the idea is we will start from the very basic step. We'll say that we can reach to the first rung. That's the first step. And from the first step, we can reach to the second step, to the second rung. And then we can keep repeating those processes to reaching to the next rung, next rung, next rung. And in that way, we can reach to the any kth rung. And if we can reach to the kth rung, then we can reach to the k plus one rung, right? So that's how we are going to prove. This is simple strategy. So what do I mean by this one is, what I'm going to do is we are going to follow some steps. The first step that I will be using is called the basis step, right? That is called basis step. The basis step is I am going to show that yes, I can reach to the rung number one, right? So I have to show, I will show or I will prove that I can reach first rung, right? First rung of the ladder. So if I can reach that I have proven, then in the second step, what I'm going to do is I will set up my induction hypothesis. And the induction hypothesis is, let me just write it here, induction hypothesis. So the induction hypothesis would be like, I have shown that I have reached to the rung number one, then I can reach to any arbitrary kth rung. So in the second step, I will repeat the basis step, right? Basis step, and will claim I can reach kth rung of the ladder, right? So that is my claim. That is the hypothesis. And then the third step, what I have to do is I have to actually prove that hypothesis. So in my third step, I will prove, right? Prove my induction hypothesis. Let me write it in short, which is IH. So how I'm going to prove that, that's again, that's what we are going to learn with different examples. But the whole idea is, if you can show that you can reach to the rung number one, right? If you can show that you can reach to the rung number one, and from the rung number two, you can reach to the rung number, from one to two, and two to next one, and next to next one. And if you can reach any arbitrary kth rung, and then you have to prove that you can now reach to the next k plus one rung, that means you can reach any of the arbitrary you can actually climb this complete infinite ladder, right? Okay, that's the whole strategy. And now, keeping this in mind, we'll solve some questions here. We'll understand with example, right, that how we are going to prove that. So the example that I'm going to discuss at first is, let me just draw a line here so that we can see. Here we are going to learn about the examples. So my example number one, right? Example one, what we are going to show is, it says, prove that 3 plus 7 plus 11 plus so on plus 4n minus 1 is equal to n into 2n plus 1. You have to show that, the question is to prove the left hand side is equal to the right hand side for all the values of n which are greater than or equal to 1. Right? So this is the thing that we have to prove using the mathematical induction. There are many other ways to prove it, but one way that we are learning in this video is proved by mathematical induction. So what should we do? We will follow some steps. So my step number one would be, let's solve this one now. The solution of this example is to use the step number one, right? So step one is, you will say the whole thing. Let me assume that let P of n is equal to this whole term that we are looking for, that we are looking to prove. So let me say that P of n is equal to 3 plus 7 plus 11 plus so on plus 4n minus 1 is equal to n into 2n plus 1. That is what we want to prove, right? For all n greater than or equal to 1, right? So this is obviously true only when n is greater than or equal to 1. This is my step number one, that I am assuming. I'm just going to say this is equal to the P of n term. So I'm going to set up a terminology here, right? And then my step number two is to set up to prove the basis step, right? So step number two is the basis step. Basis step is that, so remember from here, the basis step is I can reach the first step of the ladder. I can reach the first rung of the ladder. That's what I have to prove. So that means I will use the smallest value of n to prove that this equation is true, right? How I'm going to do that, that is the important thing. So now what does this mean? The basis step is for n is equal to 1, I'm going to use it for n is equal to 1. Why? Because my smallest value here is, this has to be true for n greater than or equal to 1. And the basis step is the smallest step that I have to take. The smallest step, the smallest value for n here is 1. So we are going to choose it for n is equal to 1, right? Then what does this mean? N is equal to 1 means when I have 1, when I say 1, it is the first term is equal to 3, right? So that means P of 1 is equal to 3. That on the other hand side, I'm going to substitute the n value here, right? I'm going to substitute the value of the n, which is 1 into 1, 2 times 1 plus 1, right? That happens to be 3 is equal to 1 into 2 plus 1, right? So that is 3 is equal to 3. So my basis step is correct. I have shown that this statement is correct for the first terminology, for the first term of the sequence, right? So this I have shown using my basis step. The next is step number 3, which is the important step. Now, the step number 3 is to set up the induction hypothesis. Induction hypothesis. Right? What does this mean? We now need to set up this induction hypothesis. That is, I have to assume that this is true for any arbitrary k value. So that's what I'm going to do here now. I'm going to assume that, let's say I'm saying assume this this given sequence is true for the kth value. How we can show that? Assume that this is 3 plus 7 plus 11 plus so on plus for kth value, not for the nth value. Now 4 times k minus 1. Okay, so 4k minus 1, right, which is the kth value. 4k minus 1 is equal to k times 2k plus 1. Yes, we are going to change n with k because now we are assuming that this is true for k value, for the kth step, for the kth rung of the ladder, not for the nth value, right? Okay, now this is my induction hypothesis that I have set up, that this is true for kth rung. Now what I have to do, the next thing that is most important is I have to prove that now. Now what I have to prove is I have to prove that this is true for k plus 1, right? This is true for k plus 1. Now k plus 1 means if the k, we can prove it for any kth random value, then the next value it is true for that one also. So if it is true for k plus 1, that means this terminology is, this sequence is true, and this can be reduced to this general formula, right? Okay. Now, how I am going to do that is now, so we know that this is true for we have as already assumed that this is true. We have already assumed this one, right? So we have already assumed this. So the assumption is 3 plus 7 plus 11 plus so on plus 4k minus 1. So the next term I will add. If it is true for k plus 1, let me just correct this k so you do not get confused, k minus 1. So then the next term, which would be the k plus 1th term. So I will add the k plus 1th term, which is 4 into k plus 1, right, minus 1. Right? So instead, in k, I'm going to substitute k plus 1 because I'm looking for the k plus 1th step. This is equal to, on the right hand side again, I have to find the k plus 1 value. So k plus 1, so instead of k, at the place of k, I'm going to substitute k plus 1. Where 2k plus 1, for k, I'm going to substitute k plus 1, right? That's what I have to prove now. So once again, this was my hypothesis. This is my hypothesis, induction hypothesis, that it is true for kth value. And now I have to prove that it is true for k plus 1 value. In order to prove that, I have added the k plus 1 term, which is this one, right? So we have added the k plus 1 term. How we added that? Here on the left hand side, we have added the next term. And on the right hand side, we replaced k with k plus 1 value. Right? Okay. Now we have to simply do some calculation, some algebra to prove it. So let's say, for example, how we can do that. So if you observe from our assumption already, we know that this whole is equivalent to k into 2k plus 1, right? So we can substitute the value of this term now. So we already know that this is equal to k into 2k plus 1 from our assumption, right, from this line. Okay, now what we can do is we can substitute this value 3. Okay, instead of having this whole, so for this whole, I'm going to write k into 2k plus 1 for this whole, right? For this whole, I have substituted its value, which is this one, right? Okay. Now, the rest of the term is 4 into k plus 1 minus 1 is equal to k plus 1 to k plus 1 plus 1. That we have to prove now, that left hand side is equal to right hand side. If we are able to prove that, then it means this is true for any arbitrary value. This formula is correct. Right? That's what mathematical induction means. So now how we can prove that? So let's say we can simplify it and then we can solve it. Let's say, for example, if I multiply this k, with the inner term, so it is going to be 2k square plus k. And on the right hand side, let me just clean it up. So this is going to be k plus 1 minus 1, right? and on the right hand side, it is going to be k plus 1 into 2k. I'm going to multiply 2 with the inner terms, 2k plus 2 plus 1, right? Okay, so this is going to be 2k square, 2k square plus k plus 4 times k, right? So k1 minus 1 is going to be cancelled out. So it turns out that this is only the 4k now. It is only 4k, right? Is equal to, on the right hand side, it is k plus 1 times 2k plus 3, right? So 2k plus 3. Right, so that's what we have got. So now what we can do on the left hand side, let me just do some arrangement. So I'm going to say 2k square plus 4k plus k. That's all fine, right? So we have we are able to find this one, this value. Okay, let's see. What we have done is 4. Okay, so we did something wrong here. So we did actually wrong here is, okay, so this whole is incorrect. Let me just resolve this one, remove this one. We have to come back. We did something wrong here, which is this one, right? The reason is, if you see, this is 4k. So k plus 1 will multiply with 4 only, not with the minus 1. So that means this terminology we have written is wrong. So it should be 4 times k plus 1 minus 1, like this one. Now it is correct. So now let's solve it. Let's solve this one. So instead, in this place, I'm going to substitute the value, which is k times 2k plus 1 plus, this will now become 4k plus 4 minus 1. That is correct, right? Okay. On the right hand side, it is going to be k plus 1 times, this will become 2k plus 2 plus 1, right? Okay. Now, on the left hand side, if I multiply k inside, it is going to be, now, let's say it's going to be 2k square plus k plus, on the right hand side, it is, oh, sorry, this one is going to be 4k plus 4. Okay. Now it is going to be 4k plus 3, not 4. 4 minus 1 is 3, so it's going to be 3. Is equal to k plus 1 times 2k plus 3, right? Okay, now what we are going to get here is, let's just do some arrangement. It is going to be 2k square plus 4k plus k is equal to 5k plus 3 is equal to, let's multiply this terminology now. So if I multiply k with 2k and then k with 3, it is going to be k 2k square plus 3k, right? And then I have to multiply this 1 with 2k and then 1 with 3. So that is going to be plus 2k plus 3, right? So let's simplify this one. This is going to be 2k square plus 5k plus 3 is equal to 2k square, 3k and 2k is going to be plus 5k plus 3. So it turns out that we have proved that the left-hand side is equivalent to the right-hand side. Right? If the left-hand side is equivalent to the right-hand side, that means we have proved our induction hypothesis, right? So if we have proved our induction hypothesis, if my induction hypothesis is proved, then what does this mean is, that means this is correct, this is true, and we can use this formula, right? So let's see a few more examples, and then we'll come back. Let me show a few more examples here. Let's say, for example, we are asked to now, okay, so we are asked to prove something like this. Let's say the question is, example 2 that we are going to discuss in this video is, it says prove that 1 cube plus 2 cube plus 3 cube plus so on plus n cube is equal to n square into n plus 1 square whole square divided by 4. So we are asked to prove this one. So let's see how we can prove that one. So we'll use our steps. So my step number one, let me say let p of n is equal to, let me put that as a p of n, which is 1 cube plus 2 cube plus 3 cube plus so on plus n cube is equal to n square into n plus 1 whole square divided by 4. Now, what I have to do is I have to now use my basis step to prove to find the first value. So now the second thing that in my step number 2, what I'm going to do is I have to use this step, the basis step, right? So what I'm going to do in the basis step is I have to prove this for the smallest values, right? What is the smallest value? So that means this equation, given equation, is incomplete if I do not specify the smallest value. So that means this is true for all n greater than or equal to 1, right? So now here you can observe that this is a very important part of this question. If the question is given and if you are not been told that when it is true and when it is not true, like in this case, it is true for greater than or equal to 1. So the smallest value of n is 1. So that means I have to prove it for p of 1, right? P of 1, which is the first term is this one. 1 cube is equal to, on the right hand side, I'm going to substitute 1 in place of n. So you can see when n is equal to 1, right? You can also think like that, right? When n is equal to 1, I have to say that that is my basis step. So which is going to be 1 square into 1 plus 1 whole square divided by 4, right? This is going to be 1 cube is, okay, 1 cube is 1. So 1 is equal to 1 square is 1 times 1 plus 1 is 2. 2 square divided by 4, which is going to be 2 square is equal to 4. 4 times 1 is 1 and 4 divided by 4 is equal to 1. So we have shown that our basis step is correct, right? Our basis step is correct. And then the step number 3. The step number 3 is the induction hypothesis, right? So step number 3 now. Step 3, which is induction, set up the induction hypothesis. So what is my induction hypothesis? My induction hypothesis is the same. I'm going to say assume 1 cube plus 2 cube plus 3 cube plus so on plus k cube, because we are setting up the induction hypothesis for kth value, for any arbitrary kth value. So plus k cube is equal to k square k plus 1 whole square divided by 4. That is my induction hypothesis. Now, if I have set up this induction hypothesis, then I have to prove that 1 cube plus 2 cube plus 3 cube plus k cube plus k plus 1 cube is equal to k plus 1 whole square into k plus 1 whole square divided by 4. So we are going to prove it for the k plus 1 value, right? So we have set up that it is true for k plus, once again, we have set up our induction hypothesis that it is true for kth value. Then we have to prove that it is true for k plus 1 value. Then we'll assume that this is true, right? Then we will believe that it is true. Now, how we are going to prove it? The next thing. So now from my assumption, we know that this value is already equal to this one, right? So what we will do, we'll substitute this value. Let's say instead of this, what we are going to do is k square is equal into k plus 1 whole square divided by 4 plus this term that we have added, k plus 1 whole cube is equal to k plus 1 square, right? K plus 1 whole square times k plus 1 is going to be k plus 2 whole square. K plus 2 whole square divided by 4, right? That's what we are going to prove now. Left hand side, we have to show that the left hand side is equal to the right hand side. Now, how we can show that? So one way of doing this is to make this term equivalent to this so that we can write the same in the same way. So what I can do is I can take the LCM of this one. So if you remember from your high school classes, that's basically very simple. So I'm going to take the LCM of this one, which is 4 divided by 4, and then since this whole is being divided by 4, so 4 and 4 will be cancelled out, so I can write it as k square into k plus 1 whole square plus 4 times k plus 1 cube, right? So we can combine them like this one. This is going to be equal to k plus 1 square into k plus 1 or k plus 2 whole square, right? So this is k plus 1 square plus k plus 2 whole square divided by 4, right? Now, in order to make it simple and simplify, let me multiply both sides with 4. Both sides with 4, that we can simply do. So then this 4 and this 4 is cancelled out, this 4 and this 4 is cancelled out. So what is remaining is k square into k plus 1 square plus 4 times k plus 1 cube, right? And then on the right hand side, it is k plus 1 whole square into k plus 2 whole square. That is remaining now, right? Okay, now what we can do, can I do one thing? Let's say, for example, if I have something like this, on a side note, if I have something like this, x cube, I can write it as x square times x, right? That is perfectly fine. So that's what I'm going to do with this k plus 1 whole cube. So what I'm going to do is I'm going to write it like this one, k square into k plus 1 whole square plus 4 into k plus 1 square into k plus 1, right? That's what I have done, is equal to k plus 1 whole square into k plus 2 whole square, right? Okay, so what I can do now is further, what further I can do is, let's say from the left hand side, I can take k plus 1 square as a common value. So if I take this as a common value, then what is going to happen now? I can say k plus 1 square as a common, then the rest of the stuff is k square, right? K square plus 4 into k plus 1, that is remaining, right? So that we have taken here. So on the right hand side is equal to k plus 1 square into k plus 2 whole square. Now, what does this mean? Let me just simplify this one a bit further. K plus 1 whole square into k square plus, it will be 4k plus 4, right? And on the right hand side, it is going to be k plus 1 square into k plus 1 whole square, right? So from this point, you can see that both left hand side and right hand side are being multiplied with k plus 1 square. So I can divide both sides with k plus 1 square. So let me divide both sides with k plus 1 whole square. K plus 1 whole square. Let me just divide both sides with k plus 1 whole square, that you can do. And then in that case, these terms are being cancelled out. And what is remaining is k square plus 4k plus 4 is equal to k plus 1. This was k plus 2, not k plus 1. So this is k plus 2. This is k plus 2 whole square, right? Now, if you observe this, this is going to be the same. So if you open up this square, let me just do that. So it is going to be k square plus 4k plus 4 is equal to, this is nothing but k plus 2 times k plus 2, right? And then it happens to be k times k, which is k square, and k times 2 plus k times 2 is 2k, plus then this 2 times k is 2k, and this 2 times 2 is 2 square, which is 4, right? So if you simplify this, it is going to be k square plus 2k plus 2k is 4k plus 4. That turns out that it is equal to the left hand side, which is 4 square plus 4k plus 4. So we have proven that left hand side is equal to the right hand side. That means this is proved by mathematical induction, that if this was true for k, it is also true for k plus 1 value, right? That's how we have done that. Okay, we'll see a few more examples. Let's say, for example, now we are going to discuss another example. Let's say example number 3. Let me just do it here. Example 3, another example for today's lesson for mathematical induction. So say suppose it says prove 1 plus 3 plus 5 plus 7 plus so on plus 2n minus 1 is equal to n square. So it actually is saying that sum of the first n odd numbers is equal to n square. That's what it means in simple way. So now we have to prove that. How we are going to prove this? So we'll use our own strategy now. We already have seen 2 examples. So step number 1. Step number 1 is we'll say let P of n is equal to this whole term, which is 1 plus 3 plus 5 plus 7 plus so on plus 2n minus 1 is equal to n square. Then in the step number 2, I have to use the basis step, right? So my basis step would be now step number 2, which is basis step. So then what I have to show here, the first thing again, when this is true for all n is greater than or equal to 1. This will be given to you in the exam or even in the book exercises, wherever you are going to see this value should be given. Then when it is true when n is greater than or equal to 1, right? Okay. Then in the basis step, what I have to do, I have to prove that this is true for the smallest value of the n, which is same as if you can reach to the first rung of the ladder, right? So which is the smallest value. So in that case, what I'm going to do is I'm going to say when n is equal to 1, so I'm going to prove that for n is equal to 1, right? So that what I'm saying, when n is equal to 1, when n is equal to 1, for n is equal to 1, that means we have to show that P of 1, which is equal to the first term, which is equal to 1, is equal to, and the value of the n, which is 1 is square. So this is true, right? Why? Because 1 square is equal to 1. So we have shown that the basis step is true. Then the next step is to set up the induction hypothesis. So in my step number 3, step 3 is induction hypothesis, right? Induction hypothesis. So what is my hypothesis here is, I will say simply assume what I have to assume is the given value, which is 1 plus 3 plus 5 plus 7 plus so on plus 2n minus 1. And now since we are assuming and we are setting up to the induction hypothesis, that means we have to prove it for n is equal to k, right? We are going to prove that for n is equal to k. So that means here I will say that this is true for n equal to k. So will substitute n is equal to k, which is 2k minus 1 is equal to k square, right? So that's what we have to we are assuming, and then we have to show, we have to prove now we have to prove what it is true for k plus 1. When n is equal to k plus 1, we have to prove that. So how we can do that? We will add the term k plus 1 term in this one, which is 1 plus 3 plus 5 plus 7 plus so on plus 2k minus 1 plus k plus 1 term. So let me see how we can add that. K plus 1 term is going to be 2 into k plus 1 minus 1. And on the other side, it is going to be k plus 1 whole square, right? That's how we are going to prove it. Then what we can do is, now we already know that from our induction hypothesis. So this whole is going to be equal to the k square. What is this? This whole is going to be equal to the k square. That we just need to substitute. So now it is going to become to be the easy, right? So for example, what we are going to do is k square plus the k plus 1 term, which is now k2 into k plus 1 minus 1, which is going to be k, right? Which is going to be the k value, 2 into k plus 1 minus 1, right? So this is going to be something like, let me just see what we have. Okay, so okay, no. So the same thing that we have done wrong here is, this is going to be, okay, let me just correct it. So this value we have actually substituted wrong. This should be something like this, because minus 1 is not with k. So it's going to be 2 into k plus 1 minus 1, something like this one, right? You can pause and you can observe this one. And now what we can do is, we are going to substitute this whole as k square plus, it is going to be 2k plus 2 minus 1, and this is going to be equal to, on the right hand side, if you open it up, it would be 2k. Okay, this would be k square. Once again, it is k plus 1 into k plus 1, which is going to be k square plus 2k plus 1, right? So on the left hand side, if you rearrange it, k plus 1 plus 2k, and this 2 minus 1 is going to be 1, is equal to k square plus 2k plus 1. So we have shown that the left hand side is equal to the right hand side. That means we have proved that this formula is correct. This is correct. The sum of the first n odd numbers is equal to the n squared, right? Okay, we shall see some more examples here. So let's say, for example, let me just go to this place and we can show up our example here. So we are going to see example number 4. Say example 4. It says, prove that, what is that? The sum of the first n natural numbers is equal to n into n plus 1 divided by 2. That means it is going to be something like that. It could be given like this one. I is equal to 1 to n, n into n plus 1 divided by 2. So you can get the question like this one, or you can actually write it, this is nothing but the sum of the first n natural number, which is going to be 1 plus 2 plus 3 plus 4 plus so on up to n is equal to n into n plus 1 divided by 2. You can even write it like this one. So now we are interested to prove it, right, by mathematical induction. My step number 1, right? So the step number 1 is the same. Let P of n is equal to 1 plus 2 plus 3 plus so on plus n is equal to n into n plus 1 divided by 2. This is my my assumption now, the first step. The step number 2 is my basis step, right? Which is the basis step. Basis step. Now, you will ask, if it is true, then when it is true? It is true for all n values which are greater than or equal to 1, right? Again, once again, it may change, but luckily in all the examples that we are doing, it is going to be 1. But you will see there are many. We shall see one example with different n values as well. So the basis step is when n is equal to 1. So when n is equal to 1, what I have to show? So That means P of 1 is going to be 1, which is the first term, is equal to, I have to substitute the n as equal to 1 on the right hand side, which is 1 into 1 plus 1 divided by 2. That is going to be 2 times 1 into 2 divided by 2, which is going to be 1. So we have proved that our basis step is correct, right? So we can we can generate the first term using this formula. That's what does it mean. Another way. Now, the step number 3 is the induction hypothesis, right? Step number 3 is to set up the induction hypothesis. What is my induction hypothesis here? So I'm going to say assume the whole term, which is 1 plus 2 plus 3 plus so on up to n, right? So now, since I'm setting up the induction hypothesis, it is not going to be n. That means the induction hypothesis is I have to prove that n is equal to k, right? For n is equal to k value. So 1 plus 2 up to k is going to be k times k plus 1 divided by 2. That is my induction hypothesis, that I can generate any random kth number with this formula. Or you can say this is actually true for any random kth number, that sum of first k numbers is equal to this formula. And then in that case, what I have to do, I have to show that I have to prove now for n is equal to k plus 1, right? So then I have to prove it for n is equal to k plus 1. And now how can I prove it for n is equal to k plus 1 is simple. Once again, 1 plus 2 plus 3 plus 4 plus so on plus k. Then I have to show it for k plus 1. So I will add k plus 1 term here, k plus 1, right? So for the k plus 1 term is equal to, on the right hand side, instead of k, I'm going to substitute k plus 1, right, into k plus 1 divided by 2, right? Okay. Now, how we can simplify this one? We already know from our assumption, from our hypothesis, that this value is equal to this one. That means this value is equal to this one. So fill up this value. That is what? K. So that is what? K times k plus 1 divided by 2 plus the kth term. K plus 1 is going to be equal to k plus 1 times k plus 2, right, divided by 2. All right. And now what we can do is we can see, we can make it now equal. How? I can write these both terms as k into k plus 1 plus 2 into k plus 1 divided by 2. How we have done that? We have already seen one example, similar example. You actually multiplied this term with 2 and divided it by 2, nothing else, right? Or in other words, you have taken the LCM of these two terms. And on the right hand side, it is going to be k plus 1 into k plus 2 divided by 2. So you can multiply both sides with 2 to make it simple, right? And then these 2's are cancelled out. So the remaining terms are now k into k plus 1 plus 2 into k plus 1 is equal to k plus 1 times k plus 2, right? And from the left-hand side, I can take k plus 1 as a common value. So if I take k plus 1 as a common, so what is remaining? Remaining part is k plus 2, which is exactly equivalent to the right-hand side, k plus 1 and k plus 2. So that means we have proved that this is correct, right? So this is proved by mathematical induction that this term is also correct, right? Okay, now we shall see one more example before we move forward. Let me just write it over here. Example number 5. Example 5, the proof by mathematical induction. It says prove that what is that is 1 plus 2 plus 2 square plus 3 square plus so on plus 2 to the power of n minus 1 is equal to 2 to the power of n minus 1. So the difference is here the minus 1 is on the left hand side, minus 1 is in the exponent. On the right hand side, minus 1 is not in the exponent. Okay. So we are asked to prove that this is true. Prove it by mathematical induction. So what we can do, we can simply use our induction steps. We can say step number one. Step number one is simple. P of, or we can say let P of n is equal to 1. Okay, I can actually write, you can observe it like this one. It is nothing but, if you observe this one, it is 2 square. Then this is 2 power 1. Then this is 2 power 0. We can write that, right? So I can actually write it like this one. This is 2 to the power of 0 plus 2 to the power of 1 plus 2 square plus 2. Okay, this is 2 cube, not 2, 3. So it is 2 cube plus so on plus 2 to the power of n minus 1 is equal to be 2 to the power of n minus 1. So that's what I'm going to prove, right? This is my first step. So the step number 2 is, okay, another thing. This is true for all n greater than or equal to 1. Once again, right? For all the values of n which are greater than or equal to 1. So the minimum value of n happen to be 1 only. Okay, for now, the step number two is the basis step. So my basis step would be to prove it for the smallest value. So the smallest value here is n is equal to 1. So that I have to prove, right? For n is equal to 1. So that means what I'm going to do is P of 1 is going to be the first term, which is 2 power 0 is equal to right hand side. I will substitute n is equal to 1. That is going to be 2 power 1 minus 1, right? So 2 power 1 is 1 and 2 power 1 is 2 minus 1, which is going to be 1 equal to 1. So my basis step is correct. So I have proved that my basis step is correct. Then what I have to do in the step number 3, I have to set up my induction hypothesis, right? My induction hypothesis. Now, what is my induction hypothesis? In this case, again, we'll write it similarly. Let's say what I'm going to do is assume that, so induction hypothesis is when you are going to prove it for n is equal to k. We are going to say that the value of the n is k now. So what we can do is we can say that assume 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 cube plus so on plus 2 to the power of k minus 1 is equal to 2 power k minus 1. That's what we have to assume. That's my assumption. And then what I have to do, then prove for n is equal to k plus 1, right? Now, if this is true, I have to prove it for k plus 1 value. How I am going to prove that? So we already know that we will find out the k plus 1 term here. I am going to find the k plus 1 term. So which is going to be now, let's say I'm going to write it here, k plus 1 term, that is 2 power 0, 2 power 1, 2 square plus 2 cube plus so on plus 2 to the power of k minus 1. Then the next term would be 2 to the power of k, right? Isn't it? What does this mean? If the k minus 1 is the term, the next power would be k. The next power would be k plus 1. So, or you can assume like that, by the way, instead of k, you are going to substitute k plus 1 minus 1. Okay? That turns out to be the k once again. But anyways, in order to make it simple, this is this one. And on the right hand side, I'm going to substitute k value as the k plus 1. So 2 to the power of k plus 1 minus 1. That is what I have to prove. So this is going to be 2 power 0 plus 2 power 1 plus 2 square plus 2 cube plus so on plus 2 to the power of k minus 1. Then this is to be k plus 1 minus 1 is 2 power k is equal to 2 to the power of k plus 1 minus 1. And now one thing that we can observe here is we know the value of this whole, right? We know the value of this whole. What is the value of this whole? Which is this one, right? As per our assumption that we have assumed from our induction hypothesis, right? So this whole is going to be equal to that. So I'm going to substitute that value. So now this is going to be 2 to the power of k minus 1 plus 2 to the power of k is equal to 2 to the power of k plus 1 minus 1. That I have to prove, right? So how can I do that? So what should I do here? So let's see what we can do is, so let's say, for example, let's say I can write here, let's say let x is equal to 2 power k. If that is true, can I substitute x here? Let's see, x minus 1 plus x is going to be 2 power k plus 1 minus 1. Okay, then can I summarize x plus x is equal to 2x minus 1 is equal to 2 to the power of k plus 1 minus 1. Is that correct? Yes, it is correct. Then now substitute back the value of the x, which is 2 power k. So that is going to be now 2 times the value of the x, which is 2 power k minus 1 is equal to 2 power k plus 1 minus 1. That's what we have now. So now one more thing here. If you have x plus x, right? So this is going to be 2x, right? So, but then you have x times x. It is going to be x square. Why? Because when you are multiplying the two numbers who have the same base and the different exponents, those exponents are added up. So the same case is true here, right? So we have same base, which is true, but which is 2, but the different exponents. So can I write this as 2 with the same base and the exponent? His exponent is 1, right? The exponent of 2 is 1. The exponent of the second 2 is k, which is going to be k plus 1 minus 1, which is exactly the same value that is on the right hand side. So hence we have proved that this is true, which is true, which is this one. That is this one. This is true, right? So we have proved that this terminology, this term is true, right? So we have seen different examples. One more example before I end up this video. So let's see how we can do. Let me just write it over here. So we are going to solve one more example to prove by mathematical induction. So example 6, right? So we have a lot of other examples available here. Let's say it says prove that, say prove that what one, it's actually the similar example. Okay, so by the way, we have done this, so it's almost the same thing, right? So but yes, it is the same thing, but with a bit difference, right? So a little bit difference. So say a little bit difference. Let's say, for example, prove that 1 plus 2 plus 2 square plus so on plus 2 to the power of n is equal to 2 to the power of n plus 1 minus 1. And this is true for all n greater than or equal to 0, right? This is true for all n greater than or equal to 0. That means the smallest value of n here is now 0. So how we can do that, how we can prove it, we already know. So we can do that. The step number one, what is the step? My step number 1 is, let me say, let P of n is equal to 1 plus 2 plus 2 square plus so on plus 2 to the power of n is equal to 2n plus 1 minus 1, right? So that's my, and now I'm going to set up my basis step. So my basis step is to see that whether it is true for the smallest value of n or not. The smallest value of n is equal to 0. So I'm going to use the smallest value of n, which is 0 now, right? And then I will find it out. If I substitute n of 0, that is going to be p of 0 is equal to the first term, which is 1, should be equivalent to the 2 power, when I substitute n as equal to 0 plus 1 minus 1. So it happens to be 1 is equal to 2 power 1, which is 2 minus 1 is going to be 1. So we have shown that this is correct, right? So this is correct. My basis step is correct. Okay, if my basis step is correct, then what I have to do, I have to set up my third step, right? This is step number 2, the third step, which is induction hypothesis, right? Setting up the induction hypothesis. The induction hypothesis is, or the let's say what I'm going to say is, induction hypothesis is when n is equal to true for the k value, right? So what I'm going to say, assume this is true for n is equal to k, which is 1 plus 2 plus 2 square plus so on plus 2 power k is equal to true for 2 power k plus 1 minus 1. Right? Okay. And then what we need to do is we have to prove that, then prove for n is equal to k plus 1, right? We have to prove it for n is equal to k plus 1. What does this mean? We will substitute the value of the k plus k. We will find out the next term. So then it means it is going to be 1 plus 2 plus 2 square plus so on plus 2 power k. The next term would be 2 to the power of k plus 1, right? The next would be 2 to the power of k plus 1 is equal to the 2 power k plus 1 and plus 1 from the, so we just substitute the k value as a k plus 1 minus 1. Okay, now what we will do, we'll simplify this one. How do we simplify this? We already know that this whole is equal to this one, right? From our induction hypothesis. So now if we know this, what we are going to do? We are going to substitute it. How? So 2 to the power of k plus 1 minus 1 plus 2 to the power of k plus 1, right, is going to be equal to 2 to the power of k plus 2 minus 1, right? That's what we have done here. Now, this is again the same thing. By the way, we have seen that. Let's say, for example, let x is equal to 2 power k plus 1. Then I'm going to substitute it here, which is going to be x minus 1 plus x is equal to 2 to the power of k plus 2 minus 1. Then it is going to be 2x minus 1 is equal to 2 to the power of k plus 2 minus 1. Substitute the value of the x back. Value of the x is 2 times 2 to the power of k plus 1 minus 1 is equal to 2 to the power of k plus 1 minus 1. And here we have 2 to the power of 1, and the bases are same, exponents are different. So we'll just add the exponents when the base is same. This is going to be 2 to the power of k plus 1, which is k plus 2 minus 1, which is exactly equivalent to the right hand side, which is 2 to the power of k plus 2 minus 1. So we have proved that with the help of mathematical induction that this is also true. So let's summarize this one. What we have done, we understood about, we discussed about the mathematical induction, right? What we do in the mathematical induction, why do we use this? We use this to prove different proofs, different claims. We need to use it to prove the claims, right? Whatever we are going to claim. So how to do that? What we are going to do, first of all, we'll solve it. We'll prove it for the smallest, prove it for smallest value, right? Prove it for smallest value. Then after doing that, set up or solve it, prove it for, solve for basis step for the smallest, so which is actually the smallest value. Sorry, we already have done this, the smallest value, which is the basis step, right? Basis step. And then use the induction hypothesis, set up the induction hypothesis, for n is equal to k. And when you do that, prove it for n is equal to k plus 1. So in other words, you can say that in the basis step, what you are going to do is you are going to set up that p of 1 is equal to true. That is what you are going to set up, right? For the first value of n, it is true. Then you, in the inductive step, or where you set up the induction hypothesis, and then you are proving the induction hypothesis, you are going to say this is true for kth value. That implies that it is true for k plus 1 value as well. That's what we do in the mathematical induction.